delighted to welcome to our Wilson Forum today a former colleague of mine from Exponent and a very good friend, Piotr Moncarz, who is now one of the co-founders of XGS Energy, which is examining the use of high temperature water produced in very deep geothermal wells as a means of electric generation. Now, this group heard from the home energy efficiency team, HEAT, back in October, and they talked about using ground-sourced heat pumps to heat, essentially using the ambient temperature of the earth to heat and cool buildings. This is another dimension that we're going to hear about today. And so, Piotr, I'm just delighted to have you join us, and we look forward to getting a slightly different view of geothermal energy and electric generation, but we welcome you here and glad to see you. I should mention to everyone that Piotr is today in Warsaw, Poland, as he meets with us. So this is a long distance proposition for him, and Piotr, we're just delighted to have you here this morning. Thank you. Floor is yours.
Thank you very much for the invitation. Just from the few voices that I hear before my talk, I am totally stressed out. The audience here on the screen is just so much more scary than my PhD committee, and I hope I can stand the pressure. But going back to what Ron said about my current professional hobby, I would call it, my current professional hobby, how to deliver to the world energy that will be both renewable, sustainable, clean, no CO2 needs to be captured, no water needs to be used, and no damage to the source of the energy left for the future generation to clean. So that's sort of just a minor task ahead of us as a society. And if you allow me, my background is, needless to say, since I had the honor to work with Ron at Exponent, my background is engineering. So as an engineer, I can hardly talk about any topic without pictures. So if you allow me, I will share some pictures with you. I will go share screen. So after some lengthy career of working in failure and failure prevention, I was getting more and more into energy questions.
Yeah.
And then I realized that the biggest failure of our society is the failure of addressing the energy issue. And I started getting deeper and deeper into energy. And eventually, with my co-founder, now long time retired, we figure out that getting to geoheat in a way different that has been done for thousands of years, in other words, getting the geoheat without getting water out of the ground is the solution. Because when we start talking about the temperatures that we need to have base load energy, the temperatures are very high, and at those temperatures, finding water sources in large quantities is not feasible. There are such places in the world, few and far in between, therefore it's not a solution. So we started concentrating on the source that is everywhere, wherever you are standing. You drill down, and depending where you are, eventually you get to hell. And now you have to figure out how to get the heat out of hell to the surface. That's it. Straightforward. So that was the beginning of the company, which is now called XGS Energy. Initially, I called it Geothermal Solution with singular solution. I was sufficiently arrogant to claim that this is the only solution. So Subsequently, my partner said, well, there is a limit to arrogance. Let's name it something that will not be rubbing everybody the wrong way. So we named it XGS Energy. Everything is X nowadays. The cars are X. The solution to airplanes are X. So we are now XGS Energy. Okay. So I know it's trivial to bring this to attention of such esteemed audience, but let's not forget this chart. And this chart is not going to change very soon. And big portion of the growth in this chart comes from countries that don't even have access to energy, let alone renewable energy. And through the telephones that we gave them and other means, they now know that there is a better life than what they had yesterday. So they want to get to the life that will be more comfortable, more higher quality, and that will require more energy. So not only the curve is growing in numbers, but the demand of energy from every increase on this curve is much larger than the average that we know in our comfortable Western world. So the challenge is for us how to develop the lowest cost, fastest to market, emphasis on cost. There's no way we can develop stuff, whether DOE or the labs of Stanford or MITs or other esteemed places, that will be fantastically clean, beautiful, but will be so expensive that the world that I just talked about will not be able to afford. It has to be environmentally sound, reliable, inexhaustible, and one more thing that is missing here, cannot rely on water, because water soon will be sold in barrels like oil if we don't solve the problem how to go to desalination with energy that is priced correctly. So it's a closed loop. We have to have a system that doesn't need water, and then that system will allow us to desalinate water to produce food, to be able to take shower for longer than 1 minute. So those are the places here that are the hot places. As I said before, you can get to hell from any place on Earth, but some places are closer to it. And so the Pacific Rim, of course, is not, no wonder it's called the Rim of Fire or the Ring of Fire. Then there are locations between the continental plates where they are rubbing. Basically, those are boundaries of the plates. And sometimes within the plate, you have an outcrop of heat. Hawaii is one of them. Japan is another one. Those are the places that are very hot too, although they are not in the boundary of a plate. Elsewhere, this is how it looks. 50% of the population of the world lives within 10 kilometers of 450 degrees C. 450 degrees C is pretty respectable temperature already for professional generation of electricity. I am sort of talking about electricity, but I want your mind to keep on issues other than electricity, like district heating and district cooling. A lot of places in the world today inherited pretty robust and reasonable district heating systems. Now, with global warming, maybe we should start thinking about district cooling. But the cooling and heating are operated with a very simple element called heat. I use this word element slightly in a joke because I studied what does the US law define heat as? And you will be surprised and probably laugh. Most of the books say that heat is a mineral. Now try to deal now with lawyers on that issue when you try to establish how much you have to pay for that mineral. They did not have the chutzpah to call sunshine mineral yet, but they will get there. Okay.
Yeah.
Okay. So 95% of the population of the world lives within 20 kilometers of 450 degrees. You say 20 kilometers is a hell of a deep hole. 10 kilometers is not that deep anymore. We are drilling already. We have drilled holes deeper than 10 kilometers. Too expensive to deliver electricity to my home, but doable. Now, too expensive, but MIT has a program now on new drilling technologies.
Yes.
And they are promising us that within the next few years, up to 5 years, we will be able to drill to 10 kilometers within speed of 5 to 10 times faster than the old grinding speed, and with a fraction of the cost. Wow, that will be hot. Now there is another challenge. You have a 10-kilometer hole, and if you want to case the hole, we better figure out how to case it different way than with heavy-duty steel pipes that the oil and gas industry is so fond of. That's too expensive and too heavy. So challenge for those of you who are material scientists, please give me a material which is conductive, strong, and lighter. Okay. And so, you know, not a big challenge after all, with the brain power that we have on this call. Okay. This is another map. It's a low quality map. I couldn't get a better one. But what this map tells us that we already know today with reasonable certainty what are the areas where we have to go 3 to 5 kilometers to get 450 degrees. Such areas are Japan, Hawaii, parts of California, the Red Sea coast of Saudi Arabia, and I could go on and on. There are plenty of places. I mean, Japan is an example. They have a rate on energy which is about 6 times of what we pay in California. Wow, what a bonanza. If I can do it economically in California, imagine what I can do in Japan. But there's a more important aspect from me. When I talk about energy, I say, if we solve the energy problem, which means it will allow us to also solve the water problem, we solve the majority of sources of wars that the world experienced for over 1 century now. They were energy-driven, access to energy, from time to time water-driven, but mostly energy-driven. Imagine what an improvement to quality of life when we don't have to kill each other to have access to energy. We have Mr. Putin will have no weapons to blackmail us with. I mean, the chutzpah with which he behaves comes from the fact that Europe made itself dependent for a long time on Russian energy. What if Europe could draw the energy from under their feet and say, Mr. Putin, you draw your energy from under your feet, and let's see how well off we can be all. So that's very important for us to see where we can get the energy for the right price today. And if we get Japan to draw the energy for the right price from their own source, maybe we'll have to worry less about China cutting the access of energy, which has to come by ship to Japan today after Fukushima. We will be much more comfortable about Taiwan, etc., etc. So it's a big task here, very exciting task. I'm looking at it as an engineer, but I also get excited as a grandfather to my grandchildren. Maybe we can give them a world that will be less prone to a war. So at XGS Energy, we look at it as a material science challenge. Why do I call it material science? Because the rock that is so hot and from which I am trying to get the heat, not through convection, but through conductivity. That rock is a very lazy conductor. It really has low conductivity. And so only using sophisticated material science approach, I can stimulate that rock to give me the heat in faster rate. So the flux has to increase. That's it. But before I get to telling you a little bit about the technological aspects of it, I want to talk a little bit more about how much energy is sitting there. There is this wonderful study by MIT done several years ago, 3 volumes, huge. But the one thing that is, to me, exciting about this study, they went and they calculated how much energy is stored in the crust of the Earth. And if you start looking at those numbers, you can see that we have more energy than even in the geological times we could use as humanity. So there is plenty of energy. Today, the energy drawn from geothermal heat, I would call geothermal heat, although I want to stress that today it means mostly sucking water out of the rock, permeable rock, much shallower than where I am talking, much lower temperature than where I'm talking typically. There are some exceptions, but typically. And to a significant degree, rock to which we are pumping water, precious water, so that the water percolates through that rock and comes back. Well, the water is not always very obedient, and big portion of it disappears in the rock. We don't see it ever again. So again, unacceptable approach. So we have tremendous opportunity here to move the baseload carbon-free energy out of the rock. So here is the method that I described, is sort of conventional hydrothermal. The most conventional is that you drill a well and you, like in oil, you heat on a big pocket pressurized water, and that water comes to the surface, or steam comes to the surface, and everybody is happy because this is a really wonderful source of energy. There are a few places in the world, some in Iceland, a couple in California, totally insignificant the balance of energy of the world. You probably know it, but I will run you through a quiz, 5-second quiz. What is the place that produces most energy out of geothermal in the world today? Anybody wants to venture to give a wrong answer? Okay.
Iceland.
Okay, thank you very much. You at least went in the right direction. Iceland is number 2 after California. California is number 1, and it's totally insignificant. So if the number 1 gets insignificant amount of wet energy out of geothermal, then let's conclude that wet geothermal is not a solution. Even forget about the water issues and all the other issues that I mentioned. Okay. So this is the traditional. Now, when we started pumping the water out of the rock in California, this is mostly north of Napa Valley, we put 20 power plants, the 21. We put our straws into the ground, started sucking the water out of it. Boom. We depressurized the reservoir. And what did we need to do? Right now, we are operating those power plants at a 50% capacity. Some of them were shut down, couldn't operate. And we are getting wastewater after preliminary treatment from surrounding communities and pumping it into the ground, into the rock, so that it comes back as hot water. That water could be a very, very wonderful source of agricultural production. Okay. In California, we are paying, most of you are on the East Coast, I see. In California, we're paying some incredible prices for water. And yet, we are pumping water into the rock to support the plants into which we invested huge amounts of money, counting on, I don't know on what, that the water in the rock will be there forever for us. Okay, so that doesn't work. So we went into our dry geothermal and we say, okay, what we are going to do, we are going to get into the rock which is dry, deeper, hotter, every place, not dependent on water. We are going to put into it our, what we call our harvester, heat harvester. In a moment, I will explain to you what it is. It sounds fancy. And we are going to do something to the rock surrounding that harvester so that the rock has, on the average, higher conductivity. So we put rivers through which the heat flows. Somebody has double computer. Hello? Okay. Somebody has to put the computer on mute because I'm getting frightful echo here. Okay, thank you. So those are, imagine those rivers that are collecting the heat towards the mainstream, which is the borehole. And in that borehole, we have a casing, like in oil and gas, except that this is a closed casing. And we are letting liquid down. No use beating around the bushes. The liquid is called demineralized water, like in pressurized water reactor. The water gets hot and then returns through return tube, which is in the center of that casing, returns to the surface, goes through heat exchanger, goes back. Pressurized water reactor without the nuclear part. Okay, that's all that it is. No magic. The magic is in this stimulation of the rock within next couple feet of the borehole. And that's what we work on for years. And we have now the materials, we have the associated patenting necessary and so on. We run extensive laboratory measurements. We build computer codes to simulate it and evaluate how big the river has to be, how wide the river has to be, what material will work better versus another material. And so this year, we just closed financing in December, an additional round. So we have enough money, we just order the materials. And beginning second quarter, we start, we get the delivery of the materials and we start installation of our well bore. In California, in the area which is called China Lake Naval Test Facilities, and they have very robust geothermal plant there that is running into the problem that I described to you. The water has disappeared. So we are going beyond the level from which they are sucking the heat deeper, and we are going to bring heat at higher temperature. Okay, so this is how it works. As I said, the hot, cold water goes down, turns around, comes to the surface. This area is a material of high conductivity that has to be installed in some plastic form and has to solidify. So forget about cementing in traditional cement. To give you some numbers, the rock conductivity is about 4 watts per meter Kelvin, about 3 to 4. The conductivity of cement-based grout is about 1. So forget cement-based grout. We develop grout which has higher conductivity. Still, cement-based materials are a pain in the neck to install under those temperatures. Okay. So we have developed materials that the principal element of it, no use hiding, is graphite in some form. How the graphite is created into a gel-like material that solidifies with the pressure of the rock and with the temperature, but not too fast for us not to be able to install our casing. That's the magic of the entire thing. The magic is called engineering, of course. So that's the system. And so the material that we are using has conductivity up to 150 watts per meter Kelvin. Okay. With the rock being 3 to 5. So that gives us a very nice boost of the flux of the heat towards our harvester. We run laboratory tests. This is a simplistic here representation of how many parameters you have to fool with. That is in computer modeling in very sophisticated time-dependent domain. You have to look at time-dependent because as you start drawing heat, your boundary conditions of cooling down the rock move out and out. And we are not interested in what happens in the first 2 minutes after we start circulating our harvesting liquid. We are interested in what happens 10, 15, 20 years from now. Okay. So that has to be steady state for the lifetime of the installation so that we can draw base load energy. Here a little bit about what we did to verify our models, our analysis. We ran analytical computer models, and then we ran laboratory tests. Let me see whether I have a picture. Yeah. So we call it TRE, the material, so thermal rich enhancement of the rock around our harvester. Without thermal rich enhancement, this boundary propagates, cooling down rather rapidly. With TRE, the river brings the heat here. We cool much less around the borehole itself. That's our laboratory test. We installed the laboratory near Lyon in France. We have, as you can imagine, a lot of the technology of drilling, installation, etc. is Texas. But we wanted to also run some tests that we run away from we know it all industry. So we have our laboratory in France. That's what we did there. A lot of measurements with granite, with our material, with TRE material. What's the influence of various parameters? So there is a solid couple years of laboratory work. We have proven to ourselves that our analytical model, the one is analytical and the other is experimental, that they give us results that I, as an engineer, say there must be something wrong with our analysis. They are too close together. So at the green line, they are so close together, you cannot even see that there are two lines there. Okay, so I say, even if we are off by some factor in what we have done in our laboratory, is so close, we have plenty of room to be off and still be right. Okay. The rest of it is history. You get the heat to the surface, and you get about 3 to 9 megawatt thermal per harvester, and you convert it now. It's appropriate inefficiency of Carnot. You convert it now into electricity. And you have to figure out whether this particular location with that temperature and that depth is going to deliver energy at a cost that will be competitive with other sources of energy. I can assure you that no matter how much Greta will be talking about young people being outraged about the climate issue, when Greta grows up and she has to pay for the energy from her household budget, she will stop emphasizing the CO2 and she will start emphasizing which energy is cheaper. And we have to get away from it. we have to deliver renewable energy, which is competitive price on price. Otherwise, it will not work. It will be socially irresponsible for us to deliver energy that will be so much more expensive that people will say, well, climate is a tough task to handle. Okay. So those are the numbers when we convert them to electricity. But as I said, do we need to convert all of that energy to electricity? What about data centers? Now with our blockchain technology running financing, business, etc., it all goes through the ultimate energy guzzlers called data centers. AI is coming. AI will require enormous amount of energy. Okay. So in data center, about 80% of the energy is to cool the system, and only 20% is to push the electrons around. So what if I take 80% of the energy that I get out of the ground and use it into direct conversion into cooling system without going through electric? Fantastic opportunity for, I heard many of you to talk about what you are doing. What a fantastic opportunity to improve the conversion of heat to cooling. Okay. You are already pretty good today with it, but there's still a lot of room for improvement. Then you put one of those, let's say the data center is between 25 and 50 megawatt, and you take the thermal 80% with direct conversion to cooling, and the 20% you do the Carnot business of 30% efficiency or 25% efficiency, whatever. Okay, so that's a beautiful opportunity. So there are a lot of opportunities for the science and engineering to work together, how to more efficiently use heat. Ron, how much time do I have?
You have maybe another 10 minutes, and we'd like a Q&A. Yeah.
Very well. Thank you. So now we start talking money. Okay. And if you start looking at this fabulous fudge factor called LCOE, levelized cost of energy. So levelized cost of energy, as you know, is the cost of development, installation, operation. You take it over a certain number of years, okay, and that gives you the levelized cost of kilowatt hour or whatever you want to use, okay. And so the levelized cost of energy, for instance, for nuclear power plant is very low, but the cost upfront, the capital upfront is enormous. So when you look at it that way, and you live in the United States, billions, trillions, one of the colleagues is in Washington knows that those numbers mean nothing. The Congress can decide to spend it, right? Even if we don't have it. But there are countries in the world that don't have it and cannot write a check for it because nobody will accept it. So for those countries, it might not be a solution. I'm somewhat excited about the small reactors because they should cost a fraction of the cost. Unfortunately, so far, per mega capacity, they don't cost fraction of the cost in the proportion. They are still very expensive. So LCOE is the measure, and now you have to see how much capital I have to put up front versus what will be long run. Gas today on LCOE is unbeatable in cost of installation. But over time, as you start paying for your fuel, which means for your gas, and even taking political aspects out of it, and the gas fluctuates with oil, and we know that oil is going up and up in the lifetime of most people on the screen. We have seen the oil price going totally wild, okay? So gas is following it more or less in the market of fuels. So you might have very cheap installation of gas-fired combined heat, etc., gas power plant, but at the end of the day, it will catch up with you through the cost of fuel. Now, if you add to it CO2, social responsibility or political responsibility, whatever it is, that sort of kills gas big in comparison to what we would deliver. We have to drill similarly to gas to get to the heat, but we have to put a lot of harvesters because, as I have seen to you, my harvester brings me 3 to 9 megawatt heat. All right? So I have to put quite a few harvesters in the ground to put 50 megawatt power plant. Okay. If you look at this picture, look how many harvesters I needed to put to get out of 50 to 45 megawatt thermal, I get divided by 3. Let's be reasonable, okay? So if I wanted to convert it all into electricity, I have to put a lot of harvesters. So for the time being, with current technologies of drilling, I have to be in the range of 3 to 6 kilometers for 450 degrees C rock. I have plenty of those places. There are more such places that I could ever imagine being involved in installation in my lifetime. That's for sure. But when we look at the world, we have to drive the price down of the installation. Okay, so if we go to greenfield installation, we are today about $52 LCOE per megawatt hour, 35 if we go to brownfield. What is brownfield? Well, brownfield, I was talking about those geothermal, wet geothermal power plants, where the facility is already on the surface. The facility that operates basically on heat. And they have dry wells there, and they have also wells that are not productive anymore. If I go there and I go deeper, I don't have to deal with the regulators. We talk a little bit about the politics in energy. I don't have to go through this because I am extracting the energy from the same source as before. So I don't have the permitting issues. I don't have the issue of building a new power plant on the surface, and my price goes significantly down. Okay. And now I am really below gas-fired power plant in California. So the legacy of geothermal, limited energy output, capital-intensive exploration. You have to find the pocket of water, in rock that is highly permeable, because the water has to flow through that rock. And there are some methods now of fracking the rock, and there are firms that were well financed in the last couple of years in the United States. If you go into this, you will find some very formidable efforts. But there still needed water to be pumped through rock that is fractured. I'm skeptic about whether the analysis of how fast that fractured fragments of that rock will get cooled by the water pumped through it, but not my business. Water dependence and unpredictable operating cost, because you don't know whether the water will flow from injection to production. You don't know whether the rock that you are fracking will be dissolving a lot of minerals out of the water and plugging the production wells. So we need to redrill them. And I'm not talking theoretical, that is a known fact. So that one, the left column, is a history. Now we go to the right one. There is room in between. I'm not saying that there's only one solution. I gave up on this. And so if we go to new geothermal output, where we can bring energy at a significantly lower price, at a higher temperature, that we can bring it for 50 years from installation, maybe more, where the operational cost is close to zero, other than the guys who sweeps the floor around the turbine on the surface, or about the heat exchanger. Is water independent, and you can engineer it for zero OPEX, depending on the geological conditions, depending on what is the use of the heat that you bring to the surface. I am talking now to a city in Europe, well over 1 million people, and they have centralized heating plants, central heating for the entire city. And they are driving the heating from gas, needless to say, Russian gas. And they have pretty good geoheat rock conditions. Well, the analysis is being done now, how much it would cost to switch that gas off for majority of the need and keep it only for the portion of the duct curve that are not economical to cover by geoheat. Okay, so we are coming to something like only 70% of the gas will be needed. The rest can be supplied by geoheat. A wonderful opportunity is being worked on right now. So we are looking, as I said, at the other industries, enabling industries, delivering solutions. For instance, the drilling technologies. Oil and gas didn't have much interest in developing revolutionary drilling technologies, because once they got the well production well, that well was producing enormous amount of money. So the drilling cost is not so important. For us, the drilling cost is important. Okay, we go to greater depths, we go to higher temperatures. We go to higher temperatures, we would like to go to higher temperatures with a good control eventually of the direction in which we are drilling. And today's sensoring systems pack up in those temperatures. So we are having a program with a company that has developed for NASA sensors that work in high temperature and processors that we are trying to adopt to this. So there's a lot of stuff that needs to happen for this to be a solution for the entire world. Right now, it's a solution for those who pay a lot for energy and have hot rock close to the surface. That's already a big achievement. So that's what we are doing. A plant will be not larger than gas-fired power plant, because our well with multiple harvesters coming from the surface doesn't take any space. So it's a processing plant for the heat. Never mind that propaganda. And so 24/7 global scalable carbon-free geothermal energy. This is what we are proposing. This is what we are installing right now. We are working really physically on installing it in full scale. Thank you very much. And if your questions are not too tough, I will try to answer them.
Pio, thank you very, very much. I think it's very interesting, because we heard about a year ago from Paul Waskoff at MIT Plasma Fusion Center about gyrotron drilling. And I suspect you must have met and talked with Paul as well.
I am aware of the effort, yes.
Yeah.
It's called Quaise Energy. That's the brainchild of MIT.
Yeah.
It's a commercial company and a golden baby for Department of Energy. They are getting a lot of support.
Yeah.
And I'm sitting and keeping my fingers crossed for their success, because their success will be my success.
Well, I think I know there are questions, and I'm going to turn to them, but I think what you're doing at XGS is transformative in many ways, but it's also very challenging. And for example, Paul Waskoff at MIT talked about this gyrotron drilling, high frequency drilling, and he mentioned that they can drill to depths on the order of 12 miles. So my question would be, what would be the optimal, given the Earth, the Earth is 8,000 miles in diameter, so there's a lot of space, a lot of volume. But what would be the optimal location for the wellhead on a deep geothermal well?
Well, that's a very good question. Did I stop sharing?
Sorry?
Did I stop sharing? Because if
Yeah, you're
okay,
fine.
very well. So
You're
if you
fine.
remember the slide where I try to show what are the hot spots on Earth, to
Yeah,
me, what I would like to do is to really punch countries that have some evil plans in the nose, and I would like to install the system in Japan. So we will not have to worry about ships delivering energy to Japan. And
yeah,
Japan pays so much per energy, 45 cents per kilowatt hour, 40 base. So if we can install that, that's a big opportunity. And the reason Japan did not develop geothermal, also they have good geoheat conditions, is because they are very obsessed, I would say nearly religiously,
yeah,
about water in the
yeah,
ground.
yeah.
And we are going far below the level. We are not touching the water in the ground. So
Right,
there is some
right,
serious conversation with Japan.
right.
Another one is Hawaii. We are delivering most of the energy to Hawaii by ships.
Yeah. No,
So
I think what's really intriguing is unlike the conventional or traditional approach to geothermal energy, you're recirculating water that you can control. You don't have
yeah,
to hope that you'll find water where there's hot bedrock. You can control it. That's really quite an important attribute. Now, one question, one final point. What Paul described, however, when he said they were drilling using this high frequency gyrotron, they were actually melting the rock, the bedrock. And I'm just thinking that if in fact you took that approach, I wonder if you could tailor the chemistry of the bedrock while you're melting it to improve the conductivity while you're drilling the hole. Just a thought. I mean, it may be totally off the wall, but I think the potential for some very innovative approaches to drilling may ultimately turn out to be very productive.
I don't even dare to try to answer this question because this is the unknown that I don't know about. Okay, that's what happens with the rock when you melt it and then it
Yeah,
solidifies maybe as a glass. What will be the conductivity?
yeah,
What will be the stability? And maybe to me, in what they are doing is more of the worry that they will create a glass wall that will be isolator. So,
right.
but since we are going to penetrate through that glass wall, let's
Yeah.
not worry. Let them drill. Let them
Okay.
drill. Okay.
Fair enough. Let's turn to the hands.
Like
Albert, you're first.
the Texan movie, Drill Baby Drill. Okay.
Go ahead, Albert.
Yeah, Piotr, um, can you clarify to us how are you producing these branches around the harvester in which it seems like you send your TRE in the branches? Can you tell us how is that done?
Where you are pressing me to say a word that I don't like to say because that word has such bad press, but the energy independence of this country was accomplished by using that word, fracking. Except that when you open fractures for gas and oil production, those fractures have to go for a long, long way. Our fractures are short. They are wider, but short, and then they propagate. Of course, principal stresses will develop in the rock, will develop how your fracture will behave once you put the notch in. But the fracture mechanics shows that you put that notch in, you will get an opening of certain lengths. Instead of putting propels, like in shale oil and gas, they don't want that thing to close. We are putting our TRE material into those fracs and then let the rock clamp on it, squeeze it, harden, and become part of the rock, but of very high conductivity. That's how it works. There is more to that fracking because we want fractures that are wider at the beginning and so on. There are technologies that come from mining industry and so on. But those are sort of techie things that are special to our company that I would prefer to skip.
Fair enough.
But essentially, if I understand you, you're gonna first drill until you reach the area which you think is hot enough. Then you start to create the fracture while drilling, and then fill the fractures with your TRE chemicals. Is that kind of the process?
More or less, the order in which you spelled it out is not correct, but that's the end result is like you described. Yes.
Thank you.
Eddie?
Yes, actually, Ron asked one of the questions I was going to ask, which is the fact that if you're using a plasma drill, you actually glassify the rock around it, apparently, and that becomes your lining. But I don't know if anyone's developed or understands the stability as you have suggested. So maybe you have some news in that respect. The other thought that I had was that in agriculture, you have a lot of greenhouses that need heat. And you can have that summer, winter, whatever. I know when I was traveling Colombia, for example, I saw greenhouses that were probably using local energy sources. It would be lovely for them to, they wouldn't need that amount of energy really to heat greenhouses through the entire year and keep food production going. And considering the state of soils deteriorating and so forth, you hear of potato farmers, for example, who won't even eat their own potatoes because they're so full of pesticides and what have you. They sell them to McDonald's, but they won't eat them themselves. So if they can get away from a lot of these pesticides and so forth, it seems to me like the agriculture area is where it would be great to be able to provide low-cost energy and not necessarily have to drill that deep, but to be able to do it prolifically. I wonder what your comments are on that.
Well, as you were talking, I came to the end of your comment. Maybe you solve two problems. One is the energy,
Water,
and the other one, water, but also another one. What we will do with the oil industry, where if we build greenhouses that would allow us for all that efficiency, using products made out of oil, okay, that would be wonderful use of oil without that CO2 nightmare of burning oil.
Right.
So, of course, we have to control the waste afterwards, because if we let it fly to the sea, we have already few islands of that sort on the sea, so on the ocean. So, yes, any form of direct use of heat has major advantage in our system. And if you have system like greenhouses, which is steady heat 24/7, because we are going to be a base load. We cannot fluctuate. Why can we fluctuate? We could turn it on and off, right? Except that if you turn it on and off too often, you would frag the hell out of the boundary between your harvester and the rock, and you would create lovely insulator. So it has to be base load. And so the uses of baseload, I may mention data centers, municipal systems of major district heating and cooling, of course, baseload power production, greenhouses, water desalinization. Oh, everybody talks about water desalination. We'll be able to do it with sun, with this and that. Where you cannot do it really efficiently with intermittent sources of energy because your osmotic system will plug, will become inefficient if you do it in a on and off basis. So you need steady production. So we are answer to those locations where steady offtake of energy is giving you most of an advantage.
Thank you.
Tom? You're muted, Tom.
Thank you.
Good.
I'd just like to make a comment here that what you're proposing opens up so many new opportunities in light of our national grid being rather fragile and old and needing much replacement. If you could provide a large source of heat in the middle of Los Angeles with no distribution system needed, or San Francisco, or even if you had to drill extra deep on a new island next to Manhattan, it's just amazing to think of how little distribution system would be needed. And I've seen an estimate that if we really switch over to electric vehicles near totally, we would need 100 billion investment in a new grid. So it's just amazing opportunities seem to be opening with your inventions.
I'm not revealing any secret when the second electric car company in California started, Rivian. One of the things they said once they got the Amazon money and so on, they said, oh, we are going to run the green distribution of goods through the Rivian vehicles, which will be using our green energy sources. And I sort of looked at it and said, I don't see where you are going to get that green energy with the grid system that we have in this country until we start having intermittent microgrids distributed throughout the entire country. I am saying the optimal size of power plant from what I just presented to you today is somewhere around 50 megawatts, 100 megawatts. Beyond it is pushing it. Why? Because imagine the amount of spaghetti underground that you would have to control if each harvester gives you a few megawatts. Okay, that becomes monstrous with today's technology. So perfect opportunity to have those microgrids. I was participating in a proposal to NSF on restoring the independence of rural America. Rural America, which became so dependent on what the big cities decide for them that everybody escapes from rural America. So if we develop sources of energy which are more regional, then the life within the radius of the source of energy will be more reliable, more plausible. I am not suggesting that energy is the only thing that rural America has to deal with, but it is one of the important issues. Electric vehicles, yes. I drive my electric car and I charge it within the supercharger, and I don't even want to think about how much damage I am doing to the environment by being green through my green vehicle.
Yeah. Walter.
Unmute myself. First of all, the electric vehicle actually produces only about 25% of the CO2. So that's one point. But Piotr, thank you for your presentation. You show the example in your example. You've got about 60 megawatts thermal coming out of one of the wells, and I guess you're going to get about 20 megawatts electrical out somewhere on. So is your proposal to make a lot of small plants? Because I'm not sure what the usage for Los Angeles is, but I'm guessing it's probably in the order of 50,000 megawatts. So how many power plants of this small size are you going to need in a metropolitan area such as Los Angeles that has thermal sources? Of course, not a whole lot of thermal sources around here, but how many power plants are you going to need? Are you going to make larger power plants? How's that all going to work?
Okay, that's a very good question of optimization system. Of course, if you start with Los Angeles, it's like a fly sitting on an elephant. Our plant, 50 megawatts, 100 megawatts, doesn't matter. But
Right.
50 megawatts in a specific application can matter to your grid, can matter to the environment. If you calculate how many tons of carbon equivalent you are saving, etc. So there are enormous areas around the world that don't have access to energy at all. There are our typical geothermal plant in California is of the order of 20 to 50 megawatts. So it's again the same size. And the fact that I can install unlimited number of those, if each of them is economical, then unlimited number of them will be also economical. So that's the issue. So this is why I need MIT to really pull their socks up and come with that drilling stuff, because to produce such not large amount of those plants, we need to install them faster. We cannot continue drilling for days, grinding the rock. So that's a very important aspect. But as I said, in a large number of locations today, I can install it with traditional drilling economically. Now, you asked that question about Los Angeles. Let's move away from Los Angeles. Let's talk about the system of electric vehicles network for charging electric vehicles across the country, where you don't need gigawatt plant to charge electric vehicles. You need to have distributed system of plants that are 10, 20, 50 megawatts. Okay, I jokingly said to my kids, before I die, I plan to have as a plant of our sort in the center of Palo Alto, and you will not even know about it. Okay, it's a joke. It's a joke, but because of all our lawyers that of course would be after me, but that's the size of plant that is very plausible. Now, how much do you produce per single windmill that sits there? The biggest ones are of the order that we are discussing here. Those monsters, 20-story monsters, okay, where the XGS thing ain't monster, doesn't change the environment, doesn't kill birds, doesn't require water, well, and works 24/7. So there are those advantages. I'm not suggesting that this is going to replace the gigawatt nuclear reactor where it's needed. And I wish we could come to some societal agreement that Los Angeles probably should have one of those reactors built in a safe, reliable way, providing Ron and Co solve the problem of the waste, of course. Okay. The first day I met Ron, we talked about the Yucca Mountain. We still continue talking about the Yucca Mountain problem. That society is moving the speed that is not light speed. Okay.
Good. All right, thank you, Pierre.
Let's just move on a bit. I'm sensitive to the time, Piotr, and I promised you we'd end. Well, it's how many hours ahead are you? 7?
I am 6 hours from you.
6 hours. So we're approaching 6 o'clock in Warsaw and 12 noon on the East Coast, but I promise we'll finish in the next few minutes. Michael, let's go to, we have two more hands up, so let's go to Michael.
Unmute. Okay, there we.
You're okay.
I'm okay. Okay.
Yeah.
Thank you very much for the presentation, Piotr. In out in my area, Smith College is planning on spending $220 million to drill a numerous number of 800 to 900 foot deep wells connected by pipes to heat the college for a geothermal system. Do you think this is viable on a long-term basis?
If you have a college as well endowed as your college,
Oh, Piotr, we've lost you. Oh my goodness. Well, I'm not sure what happened.
of the source that are viable on a what I call industrial level. Industrial level is something that you can plug to the grid. I mean, I know that there's another university in US right now that's doing a major program like this. Those are fine. Those are boutique programs. Those are boutique programs that get grants from our taxes, of course, from the government, and they experiment. That's fine. So I think Carnegie Mellon is doing, yeah, Carnegie Mellon is doing system that is green system of energy, and they are going to have a lake that participates in it, and underground pipes and storage, and fine. Fine, that's very important for the science of understanding certain things, maybe for economy of that college, I doubt. Okay, so but in terms of solution that can be reproduced from place to place, that's not a solution.
Thank you.
Eddie, you have the last question.
Yes, my earlier question related to agriculture is really has a more generic and general perspective. Localized energy sources are of great interest to industry, and I would assume that I don't know how much interest industries have expressed, shall I say, in your project. But I could imagine even the Googles of the world, for example, for their data centers, would love to have their own power sources that are reliable, just within the zone of their buildings and so forth. Another thing that that Paul Westcott mentioned was that some of these power plants that he was talking about, geothermal power plants, could be put underground, completely invisible to the world above, which would solve a lot of issues, and having a direct connection to an energy consumer would take away any risk of a grid. So I wondered just how much you have heard from certain industry leaders like Google and so forth, who may have expressed interest in your projects.
Amazing interest in what you described. Let's start with this minor portion of our national budget called defense. Having sources of energy that are independent of the grid, the cybersecurity, etc. issues, but also the thermal footprint is of enormous interest. Our airports, our other facilities. That's number one. Number two, you mentioned Google. Google invested into. They think they are a competitor to us. Of course they aren't. But another company that is going for GeoHeat, and Google invested very heavily into it. Rivian was very interested, but Rivian said, do it next to our production plant, which happens to be in United States, in the place where the hot rock is about the deepest that you can find. I said, well, let me wait on an MIT's drilling technology, because I cannot deliver the cost that you need to have on that energy. But industry is very interested. Number of projects related to data centers. I have number of them on the desk, and they are saying, well, let's wait for your first installation. Everybody says, let's wait for your first installation.
Right.
We are doing the first installation this year. We are doing the first installation this year. And I believe that this will go like house on fire. Absolutely. Because there are so many people with whom some, not all of them, the intellectual power that we have here on the screen, that would be hard. But people who are at the decision-making positions, that they are saying, that's what we need. Just to push it through the budget of my company or my system, I need to show them where it works.
Right. Thank you very much.
I think we should bring this session to a close, and I just want to end by the following comment. Sometimes when I'm feeling very philosophical, I think about the fact that nature has been very kind to us on this planet in terms of our energy needs. It's given us fossil fuels, which we have perhaps abused or used in unfortunate ways over decades and years, but it's also given us the sun and the wind and water, which is a source of hydrogen as a potential energy medium, but it's also given us the Earth's core. And that one is the least studied and practiced at this point. And I think what you and XGS are doing is really, really important. It just has so many attributes that are appealing from a humanistic as well as from a technological point of view, that I hope you're really, really successful with this, because I think it's really quite important. So I want to thank you for joining us. I'm glad you're here today. We all appreciated your insights. Thank you very much, Piotr. Enjoy Warsaw.
Thank you. Thank you for the opportunity to talk to you. Thank you.
Take care.
All the best.
All right. Thanks, everyone. We'll see you in 2 weeks.